Welcome aboard, ladies and gentlemen, to the FRQ review. Today we will be looking at the 2016 Calculus BC number 4, which is a differential equation. So, it says, consider the differential equation dy dx equals x squared minus 1/2 y. Part A says find d squared y over dx squared in terms of x and y. Just find the second derivative. We can do that. Pretty basic stuff here. So if dy over dx is equal to x squared minus 1/2 y, then d squared y over dx squared is going to be equal to 2x minus 1/2, and then some implicit differentiation, dy over dx. And what does that get me? I'm going to actually crank him up there. That way I can get some more vertical space there. My apologies. D squared y over dx squared is going to be equal to 2x minus 1/2. And what was dy dx? Well, dy dx was this original piece of the equation here, or the differential equation. So we can do plugging in the x squared minus 1/2 y into part A, and I believe we are going to get full credit for that portion of the answer. Let's keep moving. It says, let y equals f of x be the particular solution to the differential equation whose graph passes through the point -2, 8. Now, I know what you're thinking. Let f of x be the particular solution. We have an initial condition. Let's go ahead and separate terms and solve for y. That's what we've been trained to do, right? But we're not going to do that because remember, these questions, they are designed to mess with you. They know what you know, and they know how you will react when you read certain words in a sequential order. At no point in Part B did it ever ask you to separate terms and actually solve for f of x. It's asking you, does f have a relative min, a relative max, or neither at -2, 8? And we have to justify our answer. So what's that going to look like? Well, this is going to require a tool we haven't talked about in a very, very long time, because our differential equation is x squared and y. We can't really get, this to equal 0 with any kind of defined zeros in this quadratic equation right here. So sign testing is really out of the question. What they've done in Part B, and very cleverly, in a very crafty way, they have hamstrung you into using the second derivative test, which we rarely ever talk about, and it's something that we always tend to forget right as soon as we need it. So let's go ahead and bust out our second derivative test real quick here. What is the second derivative test? Well, it relies on two conditions. Well, first of all, I'm going to say, what is my slope at -2, 8? What is the first derivative? Well, that's going to be -2 squared minus 1/2 times 8. Well, what's that? That's going to be 4 minus, those guys cancel and becoming 4, so you get 0. So that means that my first derivative is 0 at the point -2, 8, which means we are flat, which means we are doing something that's like this or like this. Right? Because at this moment in time, the tangent line is, in fact, flat. We just have to figure out what's happening at that moment in time. We just need to know if we're going to be maximizing our value or minimizing our value. Well, how can we tell? The way we can tell is based on the concavity of the graph. If we look at this maximum's concavity, it's concave down here, which is why this produces a local maximum. If our graph was concave up at that moment in question, we would then be looking at a local min. So what do I got to do? I'm going to look at the second derivative at that exact same moment in time. So d squared y over dx squared at -2, 8, 2 times -2 minus 1/2, and then -2 squared minus 1/2 times 8. And again, where did I get this piece from? This is plugging all of these -2, 8s into my second derivative here. That's what I'm doing. Now from here, this guy here will become -4. And if we remember this guy's answer from our first derivative, he's actually 0, which means this is -4 minus 0, which means we get -4. In other words, our second derivative is negative at the moment negative 2 comma 8. So what does all of this mean? Well, because our first derivative is 0, and our second derivative is negative, this means that f is concave down, which means I feel like we're dealing with a local maximum. So let's put this into words. It did tell us to justify our answer. So we can say y over dx equals 0 at negative 2 comma 8, and I'm gonna do this in a bit of a weird way, so I apologize if this is not comfortable for you. Over dx squared, so that should read d squared y over dx squared is less than 0 at negative 2 comma 8, and therefore by the second derivative test, f of x has a local maximum at negative 2 comma 8. Now, I put down negative 2 comma 8 3 times. You probably could get away with saying dy over dx equals 0 and is d squared y over dx squared is less than 0 at negative 2 comma 8, and therefore you could find a way to make that more succinct. I know you guys can do it better than I can. So that is A and B for you. So let's go ahead and move on. I'm going to clear off the board, so give me a second. We are now ready to move on to part C. Now, if you notice, I left the first and second derivatives up here because I feel like we're going to need them. It says, let y equals g of x be the particular solution to the differential equation with g of negative 1 equaling 2. Again, just like part B, we have not been asked to separate terms and solve for anything. So unless they actually say, hey, dude, separate those terms, I'm not separating anything. The question is, find the limit as x goes to negative 1 of this nonsense and show the work that leads to the answer. Okay, I think we can do this. The limit as x goes to negative 1 of g of x minus 2 over 3 and then x plus 1 squared. Well, they told us that g of negative 1 is equal to 2, which means that if I let this limit happen, if I let x go to negative 1, this deal up here will go to 0, and then this deal down here will go to 0. 0 over 0 is a very wonderful position to be in because it sets us up for our good old buddy L'Hopital to make his triumphant return. Limit as x goes to negative 1. That's going to be g prime of x over 6x plus 1. So, once we do L'Hopitals, we ask ourselves, are we in a safe position to let the limit happen? Well, let's just find out. I mean, let x go to negative 1. 0 on bottom. I'm thinking we're not safe right now. Well, what's g prime of negative? Well, what happens to g prime of x if x goes to negative 1? Well, if I plug a negative 1 into here, let's find out what dy over dx is at negative 1 comma 2. Right? And again, where did this 2 come from? It came from this piece of information right here. Right here. That's what told me to plug that stuff in. So take a minute if you want to. You can pause and find out on your own. But I'm hoping that it's 0. Negative 1 squared minus 1/2 times 2. 1 minus 1, it absolutely goes to 0. So I think we might need to L'Hopital one more time. And so we get limit as x goes to negative 1 of g double prime of x over 6. We are in a safe position to let this limit happen because we're going to get definitively 6 on the bottom. What's g prime of x? G double prime of x. G double prime of x is this guy right here, our second derivative. So let's find out our second derivative's value at negative 1, 2 again. So we are going to have 2 times negative 1 minus 1/2 times negative 1 squared minus 1/2 times 2. And again, just like last time, this guy's going to go to 0, so he's all gone. So I end up with just negative 2. And there you go. There you have it. That is your answer. Negative 2 over 6 or negative 1/3 will be your answer. So a little bit of L'Hopital in our lives. Never hurt anybody. Part D. Let y equals h of x be the particular solution to the differential equation with h of 0 equaling 2. Use Euler's method starting at x equals 0 with 2 steps of equal size to approximate h of 1. Again, they haven't asked me to separate terms at all. In fact, if you look at the original diffie-q, we don't have the skills right now to separate these terms. We haven't taken that class yet, so all we can do is just use Euler's method on this thing. So let's do it. For Euler's method, I think I'm going to actually pause real quick and clean up the board once again because I'm going to need some space. I'm going to make a table, so give me a second. And we are now ready for part D. I've made my table, x, y, dy, dx, and new y. We will get to how to find new y again. I'm sure we've all forgotten, but it's no big deal. We can always refresh how to find new y. It says let y of h equal the particular solution to the differential equation with h of 0 equaling 2. Use Euler's method starting with x equals 0 with 2 steps of equal size to approximate h of 1. So, h of 0, here's step 1, and here's step 2. So notice how they said 2 steps of equal size. That means that there's an implied 1/2. That's one of our steps. And I know this guy's 2. Well, from here, what is new y? How do we find new y? Well, remember, new y is equal to dy dx, right, the slope, times whatever delta x you had going in, and then plus old y. So in this case, in this particular example, our dy dx will always be multiplied by a 0.5 or a 1/2. In fact, I'll just make it 1/2. I feel like that might make our lives a little bit easier. 1/2 plus old y. So let's go and find out these values. So what's dy dx? Well, I can let you guys figure that out. I mean, dy dx is just plugging stuff in. You end up getting negative 1, just to save a little bit of time. That ends up becoming negative 1 times 1/2, again, so that would be dy dx times delta x plus old y would be 2, and that's going to get me 3/2. When you plug 1/2 and 3/2 into the dy over dx, you end up getting negative 1/2. And then new y would be dy over dx, which is negative 1/2, times delta x, which is 1/2, plus old y, which is going to be 3/2. So that's going to be negative 1/4 plus 6/4, and you end up with 5/4. Please don't do anything here. This is nothing. You don't do this. 5/4 is your answer, which means h of 1 is approximately 5/4. And that just about wraps it up for this video. Go ahead and leave any comments or questions in the comments section. I would love to hear from you. Yeah, that just about wraps it up. I will see you in the next video.